And the comprehensibility, is it easy to follow? So far, I think it's not tough, right? So you will learn some aspect of magnetic recording. Now let's move on to the next topic. So again, today I'm like giving you bits and pieces, like cutting vegetable kind of thing today. So when I was your age, again, I used to carry a Walkman to play music. So if I want to play games, then I should have a gaming device. Then if I want to watch movie, then there's a video. Yes? No audio. Hmm. Okay, yeah. So if I have to shoot, take a photo, then I need to carry a camera, all those things, right? But now we can do all those things, all the things that we used to do with many different gadgets, with one gadget, which is your smartphone. Okay. So a smartphone can play music, it can shoot video, it can shoot photos, and you can play games, you can call people. All these were possible because of the concept that we learned this morning. So we were talking about Moore's law, right? So Moore is the co-founder of Intel. Intel is the one that makes the processors for your computers. So in 1965, Moore predicted, he observed the trend that the transistors, number of transistors in a given chip was increasing twice every year. Okay. Then he predicted that this is how we should grow the semiconductor industry. That means we should try to pack double the transistors every year. Okay, so if you have like 1 million transistors today, next year we should have like 2 million transistors and so on. Okay, so this is something that he predicted, and this has been going on for many years. Okay, so until you can see until 2005, people are just following this Moore's law. Okay, the number of transistors that we have in a chip are doubling every year. So this has been possible due to the improvements in the lithography technique and also the semiconductor technologies, materials, physics, all those things led to this kind of progress. Okay. So because this progress, we have so many benefits. Okay. So in the past, like your computer has to be like very big, but now your computer is small because you can make small processors that can do almost similar job or better job than the previous processor. Okay, so miniaturization was possible, and performance improves because you have more transistors in a given chip. So your chip is fast; it can do many more operations and so on. Then it can save power, and since you are packing more transistors in a given chip, the processing cost is the same. Okay, the lithography is the same. The chemicals that you use for making transistor, the price is the same. Okay, but you pack more transistor in a given area. That means the cost you pay for every transistor is going to be reduced. And the new functions. So new function means previously your computer cannot play music. Okay, long ago. So in 1980s, the computer cannot play music. It can only do computation. But now your mobile phone can do so many things, right? So all those new functions were possible because of the following of Moore's law. Okay. So if you look at the number of bits in a micro SD card, for example, in 2005 you could store only like 128 megabyte, and 10 years later you could store 128 gigabyte. Okay, so 1000 times increase has happened. So this is like the 10-year challenge that you guys have in social media, right? So this is a 10-year challenge for the memory. Okay, so it has grown like 1000 times in 10 years. So all this is possible because of this Moore's law based growth. But as I mentioned during my introduction today, this cannot go on forever. So Moore's law also will face limitation. So there are many bottlenecks, and because of this reason, the semiconductor industry started looking for alternative technologies. So we cannot rely on just silicon based semiconductor technology. We need to look for many other candidates. So one such candidate is a spin based system. Okay. So this is a very blue sky proposal. So people who are working on magnetism, they propose that you can make random access memory based on magnetic material. You can make logic based on spintronics material. That means you can replace the semiconductor technology completely with the magnetic materials. This is a dream, but I don't think this will happen in the near future. But if you go towards some other area where it's possible that you can replace some memory with the spin concept. Okay, so instead of SRAM, for example, SRAM is the static RAM, right? Static random access memory. So people are thinking of replacing static random access memory with something called SOT random access memory, spin orbit torque random access memory, which you will learn later. So people are looking at some alternatives like that. And this morning I told you that MRAM has already replaced eFlash. eFlash is also one kind of memory that you can find in your watches, phones and things like that. So MRAM has already replaced eFlash, but we are looking at using spin based concepts to replace or make it better, make the semiconductor technology better. So that's where the Spintronics is coming in. So what is Spintronics? You will learn more and more in detail, but as a beginning, I can give you this cartoon kind of expression. For example, you take your phone, current phone. Your mobile phone is only silicon based electronics, almost no Spintronics design here. So in this case, you send electrons, it goes through the transistors, capacitors, resistor, whatsoever, and it comes out as electrons. And you don't distinguish the electrons. Okay, so there is like some electrons flow in, they come out as electrons. So you don't distinguish between the electrons. Okay. On the other hand, this cartoon, I have two colors for electrons. Okay, I have a red color, I have a blue color for electrons. So now this is a Spintronics element. Okay, so you can notice that one type of electron, the blue type of electron, comes out more compared to red type. Okay, so now you can see that in this concept there are two types of electrons, and you have selectivity. So you can send one type of electron more preferably through your Spintronics elements. Okay, this is a very key cartoon level explanation of Spintronics. And later, as we go more and more deep, you will learn what this blue and red color means. Okay. So, I mean, to give you some analogy, for example, if you want to count the population of a country, you can say India has 1.4 billion. Okay. So you just count the number of heads. So you don't distinguish between how many males and females. So that's like the conventional electronics. So electrons, in the conventional electronics, we only consider the charge of the electron. So the electrons always have negative charge. So we only consider the charge of the electron in electronics. We don't count the other aspect, which is what we call spin. Okay, so we have studied in quantum mechanics that electrons have spin. So electrons can have upspin or electrons have downspin, and we don't consider that in the electronics, but we consider the spin property in Spintronics. So we will learn more of what is spin up, spin down, all these things. But you might have studied this already in your quantum mechanics, that electrons have a property called spin. and we consider this aspect also in spintronics. So when I show the blue color, red color in my previous cartoon, basically I mean one type of spin, for example, spin up, spin down. Okay, that's what I mean. So we consider the spin up, spin down property of electrons in the spintronics. So this has its own benefit. For example, let's say you sell cosmetics. Okay, so which company will you choose? So in one company there are like 100 males, 10 females. In this company there are like say 50 males, 50 females. Which company will you choose? Suppose you are selling cosmetic. Which company will you go to? Left or right? This one, right? Okay. So now, cosmetic is usually targeted at female. So you want to go to a company where there are more females. So in this case, this demography helps, right? So this company has 110 people. This company also has 110 people. So knowing that doesn't help you when you are selling cosmetic. But knowing which company has more females help you to sell more, right? So in a similar sense, so when you also use the spin property, so you have some additional benefit. Okay, so that's what Spintronics exploits. So when you just consider electrons have only charge, then you are losing some of the benefits that you can have by considering the charge property. Okay, so Spintronics considers the spin property also. Okay, we can have this history another time. Let me go directly to. So I'll tell you all the story of spin another day. Today we will not go into that detail. So there are many ways to explain what is spin. So one, the story which I am going to tell again another time. The spin property basically comes from quantum mechanical origin. So people wanted to explain the spectroscopy, why there are two lines instead of one line, the spectrum, all those things. So when people try to understand what's happening there, they brought this property. Okay, so they realized that electrons have this property called spin. Okay, so this is one definition of what is spin. Okay, the second definition, which is wrong but which is useful, is to imagine that the electrons spin around a certain axis. Okay, so if electrons are rotating counterclockwise, you can call one type of spin. If the electrons rotate in clockwise, you can consider as another type of spin. This is an inaccurate picture, so let me repeat. This is a wrong picture, but this helps to imagine. Okay, so we can imagine that one kind of rotation is called spin up, another kind of rotation is called spin down. This is another way to understand spin. The third way to understand spin is like, so when you talk about electrical conductivity, right? So when people studied electricity in 1700s, 1800s, they assumed that certain charges flow and the flow of charges are responsible for conductivity. Okay, they didn't know what is charge. Okay, they just brought a term that charges flow, and the flow of charges is the reason for electrical conductivity. Okay, so in a similar sense, we can consider spin. Okay, spin is responsible for magnetism. So when you say magnetism, then there is spin. So spin is responsible for magnetism. This is another way to understand what is spin. Then if all these arguments fail, all these explanations fail to make you understand, then accept spin as spin. Okay. So for example, when you studied electricity, your teacher taught you that electrons have charge. You didn't ask what is charge, right? You accepted charge as charge. So similarly, accept spin as spin. Okay. So this is how I can explain spin, and this is the meme that I use to explain what is spin. Okay, imagine a ball that's rotating, except spin is not a ball and it's not rotating. Okay, So this is a meme way of explaining what is spin. So we cannot explain what is spin using our known ideas. Okay, so spin is a quantum mechanical property. So just accept spin as spin. Okay, now earlier I draw a cartoon picture. Now I come to a bit more detail. So in the conventional electronics, we have circuits made of silicon, copper. All these are non-magnetic materials. Okay, so when you send electrons through most of the non-magnetic materials, the spin property doesn't come into picture. So the flow of electrons is spin independent. Okay, so it doesn't matter whether it's up spin or down spin. It doesn't matter. Okay, so that's why in the conventional electronics only charge plays a role. Whereas if you take spintronics elements, we'll be using some kind of magnetic material. So magnetic materials have magnetization, and there will be interaction between the spin and the magnetization of the material. As a result, the flow of electrons through magnetic materials will be spin dependent. Okay, so we are using this spin dependent flow of electrons through magnetic materials for spintronics. Okay, this is a slight deviation. Very recently, we also deal with spintronics. I mean, we observe spin dependent property in non-magnetic materials also. Okay, so this is a very recent story, but for a basic understanding, you can just consider these two pictures. Okay, in non-magnetic materials, usually the electron flow is spin independent, and in magnetic materials, the flow of electrons will be spin dependent. So almost all the spintronic devices will have some kind of magnetic material. So today your dean told you this, right? So almost all spintronic devices will have some form of magnetic material, because in magnetic material the flow of electrons depend on the spin of the electron. Okay, so in this course you'll be studying about magnetic random access memory. So in short, MRAM. So quite often I'll use the word MRAM to represent magnetic random access memory. So this is how the MRAM will be in a circuit, for example. Okay, so we have some transistor and we have a device called MTJ, magnetic tunnel junction. So this magnetic tunnel junction is the one that stores your bit 1 and 0. Okay, how it stores 1 and 0 you will learn later, but time being you just imagine that this particular device called magnetic tunnel junction stores bit 1 and 0. So this is very similar to a DRAM. For example, in DRAM you have transistor and you have a capacitor, and this capacitor may be charged or discharged, representing 1 or 0. So we store information using this capacitor in DRAM, whereas in the case of MRAM we replace this capacitor with a device called MTJ. So this MTJ can have high resistance or low resistance. So you can call one of the state as 1, another state as 0. So that's how we store information in MRAM. So MRAM basically stands for magnetic random access memory. You can also call it magnetoresistive random access memory. So in this course, you will be learning more about spin transfer torque MRAM. This is the current spintronic memory. So I told you that MRAM has replaced E-flash. So basically the memory that replaced E-flash is the spin transfer torque MRAM. And as I showed you in the previous picture, this memory part contains a magnetoresistive element. So this MTJ or magnetic tunnel junction is the magnetoresistive element, and its resistance state can be made to be high or low, representing 1 or 0. Okay, and I mean, if you summarize the benefits and problems of various memories, yeah, every memory will have its own problem and advantages. So in some areas, MRAM can be useful. That's why the industry is working on this topic. Okay, so in this course, as I mentioned, you will be learning about basic magnetism, magnetic materials, because these are the foundation for understanding magnetic recording or magnetic memory. And hopefully with the knowledge that you can have from this course, you can do your research better, or probably you can find a job in the electronics industry. So that's the main objective of this course. Any questions so far? So feel free to ask question anytime. So sometimes I'm okay. Flowing of spin is related to magnon. Okay, magnon is so in the case of magnon, you are talking about spin wave. Spin itself doesn't flow, but spin wave propagates. Flowing of spin need not be related to magnon. Okay, so later you will learn more about this, how the spins flow. All these things you will learn later. Any other question from the audience here? How long you want to go today? I have material for another 2 hours, but maybe we can spend another 1 hour or 45 minutes. Okay, so yeah. Yeah, I mean spin wave. Okay, for example, when we problem is we don't have a board. Okay, let me try to use action. For example, let's say we have a spin. This spin is precessing in certain angle. Then we have neighboring spin that has certain angle. So if you trace the path of the spin wave propagation, you will find a wave-like pattern. Okay, so that is spin wave, and the magnon is the quantized quantum of spin wave. Okay, so magnon is a concept. So it's like photon. So magnon is a quantum of spin wave, but spin is real, right? So it's a concept, yes, yeah. Yeah, yeah, no, it's okay. Yes. Yes.
When you store information on the spin of the electron, then if you make any memory device or a storage device based on it, then it would very prone to environmental magnetic influences. Like when you bring any magnetic substance close to it, the information may be lost or changed.
Yeah, yeah. So all this you will learn later. So firstly, I mean, when you talk about environment, there are two things. One is the temperature. So at room temperature, there is thermal energy, right? So Boltzmann constant multiplied by temperature, there is some thermal energy. So this thermal energy may disturb your spin, okay, whatsoever. So that's one thing. Secondly, like you said, magnet. Let's say I put my memory inside my pocket, also put a magnet, so that magnet may erase the information. So all these things we will learn later. Yeah. Any other question? So how do we understand spin wave? Is it the spin on different atoms arranged at different angles to call it a wave? Yes. And how do we understand the propagation of this wave? Okay, Magnon is not the topic of this particular course, but if you want to address this one, I can address in another class. Okay, I mean this course we are not touching Magnons, we are talking about spin, flow of spin, not the spin wave, but we can address this another day.
But it will be drawback if MRAM will be comes in the range of the magnet and that data will be get erased.
Yeah, this is a problem people are investigating. So the technical term is magnetic immunity. How you can make the MRAM immune to the external magnetic field. So this is a problem people are addressing. So if you go to say Global Foundries or some company which makes MRAM, so they develop studies to overcome this problem. Yes. But if you take hard disk drives, for example, hard disk drives you don't have this problem. Again, I'll explain why hard disk drive don't have this problem in another lecture. When we go sequentially. Okay, so when you go gradually, you'll learn that. Okay. Any other question?
Please explain that diagram, grid lines and picture and word lines, all of this.
Mm-hmm.
Capacitor versus magnet and electricity.
I mean today I'm just giving you a flavor. Okay, so you will learn all this in detail later. Because now I haven't even taught you the magnetism. So if I teach you how the NPJ works, it will be difficult. I mean, for some of you who have not learned magnetism, it will be totally difficult. So we will go with the flow. It will come in the later learning. Okay, so we are going to learn, let's say, MRAM, a bit of hard disk drive. How do we make sensors for hard disk drive, and so on. So all these things. I mean, there's some growth technique involved, technology involved. So this particular part, we'll be learning some of those bits and pieces of information. We can skip this. This one also I can see. So I talked about hard disk drive. Hard disk, there are so many processes. I'm not going through all these things, but I'll just describe this technique called sputter deposition, because this sputter deposition is the technique that's useful in the MRAM also. Okay, so let's learn about sputtering. So whether you make thin films for MRAM application or hard disk drive application, you always need something called substrate, because you are growing films with a thickness of 10 nanometer, 15 nanometer, or maybe about 100 nanometer. So those films are too thin, they cannot stand alone themselves. So you need to deposit on something solid. So that solid thing is called a substrate. Okay. So in the case of hard disk drive, people use many different substrates like aluminum alloy or glass substrates to store information. In the case of MRAM, the substrates are usually silicon. Okay, so you take a substrate, then on top of the substrate you deposit films. Okay, so how do we deposit films? So we use this process called sputtering. Okay, so what is the definition of sputtering? Okay, a simple definition is like playing billiards with atoms. Okay, so we are basically playing billiards with atoms. So in sputtering, what happens? We have material. For example, let's assume that this is a piece of cobalt, and I want to deposit a cobalt film. Cobalt is a magnetic film, right? So I want to deposit this cobalt onto the substrate. Okay, this is the, let's assume that this is the substrate on which I want to deposit cobalt. And so to achieve that, I take a target which is also cobalt. So this target I'll collide with argon atoms. Okay. So like in billiards, what happens? You have balls hit the balls, then there's a transfer of kinetic energy, right? So in a similar sense, you use the kinetic energy of the argon atoms to knock certain other atoms. So in this case, cobalt atoms. So the cobalt atoms will be ejected from the cobalt target and they will get deposited onto the substrate. Okay. So that's words, right? That's a lot of words. Usually you don't understand if I keep on saying many words. So let's use this video. So in this case, you can see the word target here. Okay. So this target is the material from where we are getting the source. Okay. Suppose we want to deposit cobalt film, then all these atoms actually represent cobalt atoms. Okay. So you have a cobalt target with a lot of cobalt atoms. So this is the target and this is the substrate on which you want to grow the film. Okay, initially to start with, this is just silicon oxide, nothing on top, but you want to grow the cobalt film on top of this substrate. Okay, so what you do, you place the cobalt target in a vacuum system and apply certain potential. So the potential is negative potential. So this target is the cathode. So it has a negative potential. Okay, so when you have applied a negative potential, let's say you have argon gas in the chamber. So let's say argon, due to cosmic radiation or something like that, argon is ionized, for example. Let's say a few argon atoms are ionized. So ionized argon atom is positive, right? Positive argon ions, they will come towards this negative target. So they will collide with this target, then knock off these atoms. So these atoms will go everywhere. So they will go here, 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 everywhere. Okay. And some of them will arrive at the substrate and get deposited. Okay. So watch the video again. So initially, oops, sorry. Okay, due to say some cosmic radiation or something, the argon has released one electron and it has become argon ion. Okay. Now you have argon ion and your target is negative potential. It's a cathode. So negative potential. So this positive argon ion will be attracted. Okay, so this positive argon ion is attracted towards the target. Okay, and this argon ion has a kinetic energy, right? It has certain kinetic energy. Because of that, momentum transfer happens. The cobalt atoms from the target gets knocked off. Okay, so this is, you cannot control the angle of this argon collision. It will happen randomly. As a result, all these cobalt atoms will go in different direction. So they will go in different direction. So the substrate is on the path of this scattering of cobalt atoms. So some of these cobalt will arrive at the substrate. Okay, so when lots of cobalt atoms arrive at the substrate, we can say you have grown a film. Okay, so this is called DC sputtering. So DC stands for direct current. Okay, so you apply negative voltage to the target, substrate is grounded. Substrate, chamber, all are typically grounded. Okay, so this is DC sputtering. So this is a pictorial description of what we learned before. So you have a target, you have a substrate. These two are inside a chamber. So it's inside a, you can say, a stainless steel chamber. So this chamber has to be at a certain vacuum. So to produce a vacuum, you have some vacuum pumps. So the vacuum pumps keep sucking the molecules, gas molecules inside this chamber. So you obtain vacuum, then do the sputtering. Okay. So we use argon as the gas for sputtering because suppose you want to deposit cobalt onto your substrate, there should be no chemical reaction. So you are starting with a cobalt target and you want to get cobalt film. So you don't want any chemical reaction. For example, you use oxygen, then you try to sputter cobalt, you will get cobalt oxide. Okay. Or you use nitrogen, you will get cobalt nitride. Okay. So you don't want reactive gases. So if you want to deposit cobalt as cobalt, you want some inert gas. Okay. That's why we use argon. People can use krypton, xenon also, but they are expensive. Okay, so normally people use argon for sputtering. And this power supply supplies the negative voltage to the target. Okay, target is called a cathode. Okay, it's at a negative potential. That's why it can attract the argon ions. So argon is neutral, but once you remove one electron, it becomes a positive argon ion. So the positive argon ions will go towards the target and they will knock off the atoms from the target. Okay, so this is the sputtering process. This is another video, animation again. Now it tells you the whole thing. So we have a chamber. So inside this chamber we are going to do sputtering. So inside the chamber there are a lot of gas, say let's say atmospheric nitrogen, whatsoever gas is here. So at first what you do, you pump all these gases out. So you apply, use some pump and pump all these gases out. Okay, so typically we evacuate the chamber to pressures of 10 power minus 8 torr or 10 power minus 9 torr, something like that. So after we reach very low base pressure, we can send in argon. So now argon is flowing in. So this blue color gas is argon. Okay, so we send in argon gas. Pump is also on. Okay, then we apply, power is on. Then the plasma forms. Okay, you can see a plasma, which means the sputtering is happening. Okay, so during the plasma formation, what happens is that the argon atoms knock the target, and the target atoms, shown by the red color, they go everywhere, and they get deposited on the walls also. So they will get deposited on the walls of the chamber. They go everywhere, and they will get deposited on the substrate also. Okay. So this is called DC sputtering. Any questions so far about sputtering? Yeah.
Is the sputtering is same like the PLD? If yes, then which one is preferred?
Okay. Sputtering is different from PLD. Which one is preferred? Okay, this is a very interesting question. I always criticize PLD. Okay, no industry uses PLD. All the labs in India probably use PLD because it's cheaper to buy, and for research it's okay to use PLD. But if you want to make reliable devices, for example, if you take hard disk industry, they make hundreds of million disks every year. Say billion disk every year. All disks have to perform similarly. Okay. So if you want to achieve this kind of performance consistency, then sputtering is the best technique. Okay, so in sputtering you can control the thickness, uniformity, composition, uniformity, all this uniformity you can maintain very, very well. So sputtering is the industry friendly technique, not PLD. But PLD is good for university because it's easy to build.
Second question is the cobalt in the sputtering reaching and making the film like the nucleation on the substrate, will the green 3 path will play a role in this?
Yeah, it will nucleate yes, the grain growth of the cobalt films depend on the nucleation and so on. Mean free path also will play a role. For example, if you, we deposit films under certain argon gas pressure, right? So let's say you have 3 millitor argon or 30 millitor argon. So in one case you have fewer argon gas molecules inside the chamber. So when you have 30 milliliter argon, you have more argon molecules in the chamber. So the mean free path will be different depending on the pressure of argon gas inside the cylinder, and that will affect the film quality. Film will be different, film property will be different. So if you deposit at low pressure, the film will be more uniform because the mean free path is less. The arriving atoms have more energy. So when they arrive at the film surface with more energy, they tend to form more uniform film. On the other hand, if the mean free path is low, when the atoms arrive at the substrate, they come with very low kinetic energy. So they don't travel around much. So you'll have like more rougher films. Okay. Okay. So if you are talking about Spintronics, Spintronics is an extension of silicon electronics, right? So we are using silicon substrate. So that's why we are using silicon substrate. So Spintronics is an extension of electronics. Conventional electronics, everything is based on silicon. So we use silicon substrate. In the lab, we use silicon oxide. We have silicon coated with silicon oxide. We use silicon oxide in the labs. Yes. But in the hard disk industry, we don't use silicon oxide or silicon. In the hard disk industry, as I show, I skipped some slide because we are not focusing on hard disk. So in hard disk industry, we use many different substrates like aluminum alloy, glass substrates, all these things. Depends on the application. Which substrate you use depends on the application. Yes. Yeah. Oh yes. Yeah. So if you are okay, so the process, as you understand, initially we pump out all the gas. Okay, so we reach a very low base pressure, say 10 power minus 8 torr or 10 power minus 9 torr, something like that. Then we let argon gas in. So if argon gas pressure is too low, then you cannot form plasma. So the formation of plasma, like you see in this video, is when you form plasma, basically the sputtering happens. Okay, so the plasma cannot be formed if the argon gas pressure is too low. So typically depends on your design of a sputtering machine. Some machine you can sputter at 1 millitorr or something like that. Below 1 millitorr it will be tough. Okay, so we can say minimum is like 1 millitorr or 3 millitorr depending on how the sputtering machine is designed. Yeah. If you go too low argon pressure, it will be difficult to sustain the plasma. Yes. Yes. It will go somewhere. It will be in the chamber, and it will be. It's a dynamic process. So you let argon gas into the chamber, and you are also pumping at the same time. So some argon will be going around inside the chamber, some will be pumped out. So there is a continuous flow. Yes.
Sputtering process. What happens if I reverse the direction? My target is at the top, and my substrate is at the bottom. Now the same process, I am keeping the same potential at the negative bottom. So will the gravity will play any role for this?
Gravity may not play much role because you are talking about atoms. They are like very, very light, right? Gravity doesn't play much role.
Formation in the top and the bottom, let's say
Because of certain other advantages, people choose one way or the other. For example, in my lab, all the guns are facing up, and one advantage of the gun facing up is, for example, let's say you have cobalt target, then you want to study the doping of cobalt with something. Let's say you want to dope gadolinium into your cobalt and study how the property of cobalt gadolinium will perform. Okay, so one simple way to do this is like place a chip of gadolinium on cobalt. Okay, so you have a cobalt target, place a gadolinium chip, then now you deposit cobalt gadolinium film, right? So this is easy to achieve if your target is facing up. Okay, so there is some advantage if target is facing up. There is also disadvantage if target is facing up. For example, let's say your target is facing up, you grow a lot of film, you have a shutter accumulates a lot of film. At some point of time, this will fall onto your target. So over a period of time, your target also gets contaminated from the peel that comes out of your shutter. So this problem can be avoided if your target is facing down. Okay, so there are advantages and disadvantages of target facing up or down. So in some industry they have targets facing this vertically like this, then substrate goes in between. So hard disk industry is like you have targets at the side, then your substrate goes in vertically. So depends. So which one is better or not depends on the case. Any other questions? Yes. Yeah, that is this process, PLD, pulse laser deposition. So people shine laser onto a target. So the laser generates a plasma. So that's a totally different technique. Yeah.
For magnetism related studies, other than silicon substrate, what substrate can be used?
For which one?
Magnetism related studies,
Mm-hmm.
characterization. Other than silicon substrate, what we can use?
Yeah, you can use anything.
Only silicon?
No, you can use anything. You can use anything. Depends on your application. For example, you can use a glass slide. You don't need to use silicon. You can use the slide glass, right? The one used in the microscopic glass. You can use that. So I have used that. So silicon we can use.
Quartz.
So
Quartz
also you can use. So for some studies we use sapphire. Some studies we use magnesium oxide. So depending on your application, what do you want to do, you have to choose the proper substrate. Yeah. Any other question? Okay, so far what I described was a DC sputtering. Now I move on to a slightly advanced type. It's called DC magnetron sputtering. Okay. So in the DC sputtering, we apply direct current to the target and we generate plasma. But there's a problem in that DC sputtering without magnetron. Usually you need very high voltage, around 1000 volt is needed to strike plasma. Also the deposition rate of DC sputtering is low. Okay, so to improve the deposition rate and to achieve sputtering at lower voltage, like for example 400 volt or something like that, people use this concept called DC magnetron sputtering. Okay, so in this case we have a target. Below the target we have certain arrangement of magnets. So these magnets generate a magnetic flux, or you can say magnetic field, and you know that that Lorentz force. So when electrons have certain velocity, so charged particle moving with certain velocity, and when they are in a magnetic field, they have this V cross B force. Okay, so I can show you this video to make it interesting.
So this is a evacuated tube. It's a big negative potential on this electron. So high that it actually boils the electrons come off the electron, makes a beam of electrons. It also has some ionized, a little bit of background gas that ionizes to keep everything stable and doesn't charge up too much. But mostly you have electrons flying off this electrode, and most of them go straight to this metal plate, and that's the end of the story. But there's a little slit in the plate. So some of them get through and make a beam that keeps going. So you've got a beam of electrons. And this little plate is tilted a little bit. So they slowly, along this direction, they crash into the plate. The plate has a phosphor on it, so it lights up when they crash into the plate. So when I turn it on, there you can see the beam. That's a beam of electrons flying through the tube. So what we're going to do is bring a magnet and see what it does to the beam of electrons. Because remember, this bar magnet, the field lines go from the north pole, the red is the north pole, to the south pole. So if we just think about the poles or the field right at the ends, because we're going to use the ends, it'll be this way, near the north, it'll be pointing in to the south. So I will bring the north pole pointing at me at the beam. Let's see what that'll be. We have the beam going this way, and I'm going to bring this pointing in, so we're going to have a B field like this. So V cross B also the same as this. It should be up. So let's see what happens. There's our beam, and I bring in this magnet. Oh, there's the deflection we hope for.
Okay, he says the beam should go up, right? But the beam came down. Why? Yeah, because he didn't consider the charge of the electron, negative charge, right? So because of that, there is a deflection in the down direction. So we use this. So we use this V cross B force. So what happens? Let's say now this is the target. So this is a piece of cobalt that we want to deposit. In the previous case, we didn't have the magnets below the target. Now we have magnets below. So there is a magnetic field. So when there is a magnetic field, and when now we have electrons, so these electrons will spiral around. Okay, because of the V cross B force, electrons will be spiraling around these flux lines. So when electrons spiral around here, means they spend more time. Okay, they spend more time near the target. So when they spend more time near the target, they have more probability of colliding with argon atoms. Okay, then they can produce more ions. Okay, so the spiraling of electrons lead to more ionization. Okay, so when you have more ionization, basically we are applying voltage, right? The current will be large. Okay, so this is what I'm talking about. So more ionization means we can sputter at lower voltages. So compared to DC sputtering, which happens at around 1000 volt, with magnets below the target, we can reduce the sputtering voltage to 400 voltage. And because of this V cross B force, we learned that there will be more ionization, which means the deposition rate can be increased. So we can form thicker films in shorter time using this DC magnetron sputtering.
I can actually.
Okay, so that is the concept of DC magnetron sputtering. Let's do some question before we move to the next topic. Okay, most of you are right. So, as I mentioned, substrate is a material platform to hold layers of thin film, and it can be a piece of silicon wafer, or it can be a piece of glass slide, or it can be a single crystal of magnesium oxide, aluminum oxide, anything. So, all of the above is the correct answer. Hmm. So, we skip this one. Okay, most of you are right. So, in DC magnetron sputtering, we keep an array of magnets below the target. Okay, so it will be something like this. Okay, for example, in the earlier picture I showed you, like, we have one set of magnet here, another set of magnet here. So let's say this is north pole, this is south pole. There will be magnetic flux going from this to the other side, which can generate the magnetic field needed for the magnetron sputtering. But for industry application, people don't prefer this. Okay, I mean, if you go to your lab and look at the magnetron in your lab, probably it will be like this. Okay, there is a problem with the magnet configuration like this. Can anyone say what is the problem? Let's say you have a magnet like this below your target. What will be the problem? I mean, if the magnets are strong, you can still sputter. Or if your magnetic target is thin, you can still sputter. But there is another problem with this design. What happened? Yeah. So what happens in this configuration? The more erosion happens in this region. Okay. So I mean, the magnetic field goes this way. There's more probability for electron to stay here. So more ionization in this region, more sputtering happens here. So after some time, what happens is your target will be it will be like this. Okay, let's say you look at one side. So because of more ionization here, the target will be eroded here. The rest of the target is not used much. Okay, so after some time, what happens? You will burn a hole. Then you have to throw the target. Okay, so basically you will be using maybe 20% of the target. The remaining target is spoiled. Okay, this may be okay for the labs, but if you are looking at the industry where they make many pieces of, say, memory or disk, it's not acceptable. So they want to use the target as much as possible. So to do that, they have this kind of asymmetric array. Okay, so here is symmetric, right? The magnets is symmetric with respect to any line you draw from one edge to the other edge. But here It may be symmetric with respect to this line, but it's not symmetric with respect to this line. Okay, so they use this kind of asymmetry configuration. So if this is not rotating, then more etching happens here, right? So you can see this is where the magnetic field will be strongest, and you see the etching will be mostly here. But they will use this asymmetric magnet array and rotate below the target. Okay, so when they rotate below the target, for example, it can be like this. So asymmetric array, but they will rotate behind the target. So in that case, they can erode the target more uniformly, and this can help to use the target significantly, and it also helps in achieving the uniformity in thickness. Okay, so these are some techniques people use for depositing thin films for hard disk or MRAM. I think I can skip this part. Okay, I also want to teach you some aspect of material science, because later when I talk about MRAM, MTJ, I'll be talking about some crystallographic fundamentals. So I need to introduce this one, but because it's very late now, I'll stop here. Maybe we'll continue from here tomorrow. Okay.
We talked about the GDCO, which is a ferromagnetic material.
Gadolinium cobalt is a ferrimagnetic material. Yeah, this ferrimagnetic material will generate strong orbital torques. Now we want to tune the sign and the magnitude. Can we do that by changing gadolinium content only or cobalt? Temperature of what? Temperature of deposition or temperature of operation?
So we have, if I want to increase the magnitude of the ferromagnetic particular material, so like the temperature also plays important role in that. The second thing is asking is that
temperature of deposition.
Whether the content of the GD and cobalt, if I'm varying, the magnitude will be increased or not.
Okay, maybe you can ask this question. This is about orbital torque, right? We'll be discussing spin orbit torque, orbital torque, etc. maybe on day 7. So at that time he can ask this one. Maybe I answer this question: why is sputtering of soft magnetic materials difficult as suggested? Maybe I can draw a picture. Can they see?
Yes, sir.
Okay. So let's say this is the audience in Teams. Can you see the PowerPoint? Please type yes or no. Now they can see. Okay. Let's say this is a target, normal target. Normal means non-ferromagnetic. So if you have magnets below, then these targets have not much permeability, so magnetic field will go above the target. So you'll see lots of flux lines. So with non-magnetic or materials with a low permeability, you will see a lot of flux lines above target. So you can achieve a lot of V cross B force. So sputtering is not a problem. On the other hand, if you have a ferromagnetic material, like a soft magnetic material, and you have magnet below, so because the permeability of the ferromagnetic material, most of the magnetic field from the magnet will go through the magnet, the target itself, and only few flux lines will come out. Okay. So for example, if you measure the magnetic field here, it could be like say 300 to 500 posted, something like that. On the other hand, if you use the same magnet and a soft magnetic target, here if you measure the field on top of the target, you will see that it's like 50 oersted or something like that. Okay, very low field above the target because of the permeability of the soft magnetic target. Okay, soft magnetic target conducts all the flux through the target itself, so nothing comes out, so the field is very low. So because this field is very low, you cannot sputter. So typically we need around 300 posted or more to achieve good DC magnetron sputtering. Okay, any other questions?
My question is the temperature of deposition.
Yeah, I mean, this question is related to the same thing, the gadolinium cobalt. Any other question? Okay, if not, we stop here and we'll continue from here tomorrow. So tomorrow we'll learn a bit of material science, then start learning the fundamentals of magnetism. Yeah, thank you. Bye-bye.